In this video, we will be looking at exponential equations. When we're solving exponential equations, there are a few ways to solve. One method is to establish like bases. So we're going to try to solve for x in each of these problems. First up, we have 4 raised to the x power is equal to 16. You might recognize that x has to be equal to 2 because 4 squared is 16. That's fine, you can do that. But I just want to show you what this looks like from a different perspective so that when we do the harder ones, it doesn't come as much of a shock. 4 to the x power, I'm going to leave that alone. I know that 16 is 4 squared. So now they have the same base, they're both base 4. So since they have the same base and they're equal, their exponents must be equal. So that's one place where we can get x equals 2. Next up, we're looking at 3 to the x power is equal to 243. So 3 to the x is equal to, I wonder if I can write 243 as 3 raised to some power. 3 to the 4th, that's 81, that's not big enough. 3 to the 5th is 243. So I can rewrite 243 as 3 to the 5th power. Since they have the same base and they are equal, their exponents must be equal. X is equal to 5. If you can do that one like I did on this last one and just say x equals 2, that's fine. Nothing wrong with that. Next up, we're looking at 25 raised to the x power is equal to 5. You might want to jump to the conclusion that x equals 2, but that is not the case. Notice that the exponent x is on the 25. I want to see if I can write both of these with the same base. Well, 5 is 5 to the 1st power, and 25 is 5 squared. So on the left side, I have 5 squared raised to the x power is equal to 5 to the 1st power. With my exponent rules, I know that if I have a power raised to a power, then I multiply those powers. So that's 5 to the 2x is equal to 5 to the 1st. So now they have the same base and they're equal, so their exponents must be equal. 2x is equal to 1, meaning x is equal to 1/2. Remember when we did fractional exponents? This is showing another way to prove that the square root of 25 is equal to 5. Because if 25 is raised to the 1/2 power, that means the square root of it. This last one's a little bit tricky. We have 1/3 raised to the x power is equal to 9. I can't really think of a way to turn 1/3 into 9 raised to a power, and I can't really think of 9 being written as 1/3 being raised to a power. But I do think I can write both of them as 3 raised to a power, because 1/3 is 3 to the -1 power, and that's being raised to the x. 9 is 3 squared. So that way they both have a base of 3. If I multiply my exponents, I get 3 raised to the -x is equal to 3 squared. They have the same base and they're equal, so the exponents are equal. -x equals 2. Dividing by a -1, I get x equals -2. So using like bases is one way that we can use to solve exponential equations. Sometimes when they're simpler, this can be the best way to go, but not always is this going to be the best way, especially if you can't get like bases. So another way is to convert the exponential equation from exponential to logarithmic form. So we saw when we were solving logarithmic equations, if there was just one log, then it was best to convert to exponential. I kind of think of the same idea but in reverse. If I see just one exponent, then maybe it's going to be best to try it in logarithmic form. So first up, I have 3 raised to the 2x power is equal to 80. This is one of those examples where I can't think of a way to write 80 as base 3 raised to some power. So let's try putting this in logarithmic form. If I think of it as a snail, then I will have log base 3 of 80 is equal to 2x. I just need to divide by 2. X is equal to log base 3 of 80 divided by 2. That is a perfectly acceptable answer. If you are someone who prefers a decimal answer, that's totally okay. You just have to remember we can't type log base 3 of 80 into our calculator, or at least most of us can't. So we have to use the change of base formula and make it a log of 80 divided by the log of 3. And whatever we get from that, we divide by 2. So the log of 80 divided by the log of 3 equals divided by 2. And there's your approximate decimal answer. What's really cool is we can use this and check our answer. Something I don't think I've showed you guys is a lot of us have a store button, STO arrow, and then we have some sort of variable button. So I'm going to store this as X. Now if I type X into my calculator, it knows to use this 1.994346268 number. If I take 3 raised to the 2 times x power, I get 80, and I know I have the right answer. Sweet! Next up, we're going to try 7 times 4 raised to the x power equals 31. This sort of looks like the last one, but I have that 7 out front. And I don't like having that 7 out front because my exponential is not by itself. So I'm going to start by dividing both sides by 7. That will leave me with 4 to the x power is equal to 31/7. Now it looks like the last one, and I can put it into logarithmic form. And I will have log base 4 of 31/7 is equal to x. That's good enough. If you want the decimal form, you'll have to use the change of base formula. The log of 31/7 divided by the log of 4. You can do that. Let's go ahead and check it just to be sure. So we have the log of 31/7 divided by the log of 4 equals, I'm going to store it as x. And we have 7 times 4 raised to the x power equals 31. Cool. So remember, every time we're solving an equation, we can check our answer. Even if it's complicated, it's still an option. We're going to try one more of these. We have e raised to the 1 minus 3x power is equal to 12. If I put this into logarithmic form, I will have log base e of 12 is equal to 1 minus 3x. But wait a minute, log base e, that's natural log. So what I'm really looking at is the natural log of 12 is equal to 1 minus 3x. I'm trying to solve for x so I can subtract the 1 over. Natural log of 12 minus 1 is equal to a negative 3x. And if I divide both sides by a negative 3, then I get the natural log of 12 minus 1 divided by negative 3 is equal to x. Let's check it. The natural log of 12 minus 1 divided by negative 3, I'll store it as x. And I get e raised to the power of 1 minus 3x is equal to 12. All right, this next problem is going to be longer and more tedious. So if you take up a lot of space when you write, you're going to want to start this one on a new page. But it's going to help us develop a lot of our logarithm skills. So make sure you're trying to follow along. If you need to pause the video after each step just to kind of wrap your mind around what's going on, that's totally fine. I just want to make sure you're following along with this one because it is a little bit longer. There's a few more steps, and I don't want to lose you. So we want to solve 3 raised to the 2x plus 1 power is equal to 5 raised to the 3x minus 4 power. What we've been looking at so far is when we have an exponent on only one side of the equation. Here I have it on both sides. So I'm going to use a slightly different method of attack here. I am going to think of the tools I have that allow me to get exponents to not be exponents anymore. That reminds me of Amanda's favorite log rule that says if I have an exponent in a logarithm, then I can bring it down front. So I'm going to use that idea. I'm going to start by taking the logarithm of both sides, just the common log. So we have the log of 3 raised to the 2x plus 1 is equal to the log of 5 raised to the 3x minus 4. So I'm allowed to do that kind of for the same reason that I can add the same thing to both sides of an equation, I can square both sides of an equation. As long as you do the same thing to both sides, it stays equal. Now I'm going to use Amanda's favorite log rule that says if I have an exponent, then I can bring it out front. Well, my exponent is 2x plus 1, so that whole thing is going to move out front, and I need it to stick together. So it's going to go in parentheses. So I get 2x plus 1 in parentheses times the log of 3. I'm going to put my 3 in parentheses just so I know it's the argument. And I'm going to do the same thing on the other side. This is equal to 3x minus 4 in parentheses times the log of 5. So I've used Amanda's favorite log rule to take my exponents and move them out front. What I'm going to do now is use the distributive property. The distributive property is going to let me take the log of 3 and multiply it by my 2x and my 1. And then same with my log of 5 times 3x and a negative 4. So first up, I have 2x times the log of 3 plus 1 times the log of 3 is just the log of 3 will be equal to 3x times the log of 5 minus 4 times the log of 5. So there I have distributed. Next up, I want to recognize what my goal is. I'm trying to solve for x. When I'm trying to solve for x, I need all of the x's on one side of the equation and everything without an x on the other. So my terms with an x are my 2x log 3 and my 3x log 5. Terms without an x are the log of 3 and the negative 4 log of 5. So I want all my x's on one side. So what I'm going to do is I'm going to subtract 3x log 5 over. Everything without an x I want to put on the other side, so I'm going to subtract a log of 3 as well. So that means I'm leaving my 2x log 3 alone. I'm subtracting 3x log 5 from both sides. I'm going to be moving this log of 3 over so I don't have to worry about it. This is equal to, I already have a negative 4 log 5, and I am subtracting this log of 3. So in that step, I rearranged my terms so that all of the x's were on the left and everything without an x was on the right. All right, I'm still trying to get x by itself. So I need to figure out if there is a way I can combine these in some way so I only see the x once. This step is a little bit tricky, but what I'm going to do is I'm going to recognize that on the left-hand side, I have a greatest common factor of x that I can factor out from those two terms. So if I pull out an x on the left-hand side, what I'm left with is 2 log of 3 minus 3 log of 5. I'm not going to touch the right-hand side at all, so this is equal to negative 4 log 5 minus log of 3. And to get the x completely alone, I need to divide by this thing in brackets because it's x times that equals the right-hand side. So I'm going to divide both sides by that thing in brackets. And I'm going to get x is equal to negative 4 log 5 minus the log of 3 divided by 2 log of 3 minus 3 log of 5. That is my exact answer. I'm going to walk through this one more time just because there are a lot of steps, and I want to make sure you know where each step comes from. So in the very beginning, we had 3 raised to the 2x plus 1 power is equal to 5 raised to the 3x minus 4 power. Because my variables are in the exponents, I need to figure out a way to make them so they're not in the exponents. And I know that Amanda's favorite log rule is going to allow me to do that. So that means I need to have a logarithm in order to be able to pull them down. So my first step was to take the log of both sides. From there, I took my exponents and plopped them out front. Just make sure they stick together as exponents, so you put those exponents in parentheses. From there, I distributed my logs through the parentheses. Got me here. Since I'm trying to solve for x, I want to get all of my x's on the same side of the equation. So I moved my 3x log 5 to the left-hand side, and then I subtracted my log 3 to the other side because it didn't have an x. That got me here. I then recognized that both of my terms on the left-hand side had an x, so I was able to factor that out as a greatest common factor. I factored it out, and then I divided both sides by what x was multiplied by to give me my final answer. We're going to check it just because there was so much going on here. So I have negative 4 times the log of 5 minus the log of 3 divided by 2 log of 3 minus 3 log of 5. I'm going to store that as x. And going back to the original, we have 3 raised to the 2x plus 1 power and 5 raised to the 3x minus 4 power. They are equal. And in the process of this, we got our decimal answer as well, if you are someone who prefers decimals. All right, so that's the most complicated these get. There are not many of these. Just work through your steps one by one, and you'll be all right. We are going to take a look at a couple of application problems. First up, we want to know how long will it take $10,000 invested at 3% compounded annually to earn $2,000 in interest? Well, we have to recognize that this is a compound interest problem. In the homework, it will give you the formula. But since we're not in the homework, I will give you the formula. A is equal to P times 1 plus R over N raised to the NT power. We need to figure out the value of each of these variables. Starting with A is the amount that the total investment is worth now. We started by putting in $10,000, but we've added $2,000 in interest. So now this investment should be worth $12,000. We're going to use $12,000 for A. P is the principal, which is the original amount we put in. That was the $10,000. R is our interest rate. We're told it's 3%, but we want to write it as a decimal, so we get 0.03. N is the number of times we're compounding per year. We're being told that we're compounding annually, and annually means once a year. And then T, we're not given a value for that. Our goal is to find how long, so we don't know T. So let's start plugging in what we have into the formula. So A, which is 12,000, is equal to P, which is 10,000, times 1 plus R, 0.03, divided by N, which is 1, raised to the N times T power. I'm going to simplify what that looks like because it looks pretty complicated right now. This is 12,000 is equal to 10,000 times 1 plus 0.03 divided by 1 is just 1.03, and 1t is just t. So we're looking at 12,000 equals 10,000 times 1.03 raised to the t. This looks like some that we solved in the beginning of this section. We have just a single exponent, so we want to try putting it in logarithmic form. But to put it in logarithmic form, the exponential has to be by itself. So I need to get this 10,000 out of here. I can do that by dividing both sides by 10,000. That'll give us 1.2 is equal to 1.03 raised to the t power. So if I put this in logarithmic form, I'll have log base 1.03 of 1.2 is equal to t. But if you tell me it takes log base 1.03 of 1.2 years to gather $2,000 in interest, I'm not going to know what you're talking about. I need a real life answer here. So using the change of base formula, this is the log of 1.2 divided by the log of 1.03. So the log of 1.2 divided by the log of 1.03. I'm getting this is roughly 6.17 years, because time is measured in years. So if you put $10,000 into an account that gets 3% compounded annually and just let it sit there for a little over 6 years, it will accumulate $2,000 in interest. We're going to keep working with these application problems. One common exponential growth pattern that we look at is population. So the population of India was about 1.25 billion in 2013, with an annual growth rate of about 1.2%. This can be represented by the formula P of t is equal to 1.25 times 1.012 raised to the t power, where t is the number of years since 2013. To the nearest thousandth, what will the population of India be in 2031? All right, so they gave us a formula. They told us that P is the population, and then T is the number of years since 2013. Our goal is to find the population, which means I don't know what P is going to be. They say in the year 2031, which means I know T. We have to remember T is the number of years since 2013. So to figure out what to use for T, I can take the 2031 minus the 2013. I get that T is equal to 18. I'm going to plug in 18 into this formula. P of 18 is equal to 1.25 times 1.012 raised to the 18th power. They wanted me to round to the nearest thousandth, so I'm getting 1.549. Wait a minute, we were finding population. Does that mean the population of India is going to be 1.549 people in 2031? Because that's kind of grotesque. Well, no. That's measuring in billions. So the population will be 1.549 billion, or if we write that as a standard number, it's 1,549,000,000 people. Make sure you're reading the question carefully, because I guarantee you there will be one that tries to trip you up on the homework. Next up, the function d of t equals 600e to the negative 0.00259t can be used to find the number of milligrams, d, of a drug that is in a patient's bloodstream T hours after it is administered. How long until half the quantity remains? All right, it wants to know how long, so that's looking for time. So that means I don't know T. That's the one I'm going to be solving for. My goal is to figure out how long until half the quantity remains. Well, to figure out how long until half the quantity remains, I need to know how much we started with. If you think back to when we were first writing our own exponential equations, you might recognize how much we're starting with. But in case you forgot, there's one way to check. If we're starting when t equals 0, so at t equals 0, then the amount of drug in the system, d of 0, is equal to 600 e to the negative 0.00259 times 0, and that's 600. So you might recognize that 600, the number out front of the exponential part, that's our initial value. So we are starting with 600 milligrams. We want to know how long it takes until half of the quantity remains. So when we're stopping, it's going to be half of 600, which is 300. So we want to figure out how long it takes to get down to 300. 300 is the amount that remains, and that's our value of d. So I'm going to plug in 300 for my d of t. So we get 300 is equal to, now I'm just going to use the formula, 600 e to the negative 0.00259 t. And now it looks like the last problem. I have just one exponent, so I need to get that exponential by itself. So I want to divide by the coefficient, 600. If I divide both sides by 600, I'm going to have 300 over 600, which is just 1/2, is equal to e to the negative 0.00259 t power. And now that it's just a single exponential equals a number, I can put it in logarithmic form. So I'll have log base e, that's the natural log, of 1/2 is equal to this exponent, negative 0.00259 t. So to solve for t, I need to divide both sides by that gross negative number. And I get that t is equal to the natural log of 1/2 divided by negative 0.00259. So the natural log of 1/2 divided by negative 0.00259, I'm getting that t is equal to 267.62. Remember, t is measured in hours. So it's going to take 267.62 hours to get down to half. If I divide that by 24, because there's 24 hours in a day, that's 11.15 days. This is the math that's behind the instructions on the back of pill bottles. When they say only take 2 every 8 hours or whatever it says, this is the reason why. Granted, most of the drugs that we can buy just at Walmart or the pharmacy or whatever, they don't have this long of a lasting period. But this is the math where it comes from. So I think that's kind of interesting. Next up, we have the half-life of radium-226 is 1,590 years. If a sample contains 100 milligrams, how many milligrams will remain after 4,000 years? Let's see what we can do with this. Half-life represents the amount of time it takes for an amount to cut in half. So that's what we just found in the last problem, was a half-life. We are told that the half-life is 1,590 years. Half-life problems are exponential, so I'm kind of thinking y equals a times b to the x, or since we're dealing with time, y equals a times b to the t. We have to remember that a is our initial value. Right? We know that the half-life of radium is 1,590 years. So we know that it takes 1,590 years for us to cut in half. We're told if a sample contains 100 milligrams, how many milligrams will remain after 4,000 years? Well, let's see what we have. They gave us an initial value and they gave us a time, but we don't have a b value. Let's think about this. It says if a sample contains 100 milligrams and we know the half-life. If we start with 100 milligrams, and after one half-life, we're going to end with 50 milligrams. And we know that the time that's going to take is 1,590 years. That gives me enough to plug into a generic equation. So y, which is my end value, 50, is equal to my a value, my initial, which is 100, times b raised to the t, which is 1,590 power. This is going to allow me to solve for b. Just like in the past, I want to divide both sides by 100 so that my exponential is by itself. 50 divided by 100 is 1/2. That's equal to b raised to the 1,590 power. And now we have a little trick up our sleeves. I'm going to put this problem on hold for just a second. If I told you x squared was equal to 4, you would take the square root of both sides, to plus or minus, and you'd get x equals plus or minus 2. We learned that the square root is the same thing as raising something to the 1/2 power. All right, well, I don't want to take the square root in this problem. I want to get rid of a power of 1,590. So what I need to do is take the 1,590th root of both sides, which is the same as raising both sides to the 1 over 1,590 power. What this is going to do is we have a power raised to a power, so we would multiply those powers. And that would just give us b to the first, which is b. So we're getting b by itself over here. So we get b is equal to, on the left-hand side, we have 1/2 raised to the 1 over 1,590 power. We can leave it just like that. So we now know what b is. So now we can actually attack the problem at hand. It says if a sample contains 100 milligrams, so that's what we're starting with, we know that our b value is 1/2 raised to the 1 over 1,590. It wants to know how many milligrams will be remaining after 4,000 years, so we're going to use t equals 4,000. So we have an a, b, and t value. We want to find y. So we get y is equal to 100 times 1/2 raised to the 1 over 1,590. And that is raised to 4,000 power. Well, hey, if I have a power raised to a power, I multiply those powers. So this is 100 times 1/2 raised to the 4,000 times 1 over 1,590. That's just 4,000 over 1,590. So that's 100 times 1/2 raised to the power of 4,000 divided by 1,590. What I'm getting is about equal to 17.4861, and that's measured in milligrams. So what I've done is I've started with the information that they gave me. This half-life is 1,590 years. So I know after those 1,590 years, I'll be cut in half. So if I start with 100, then at the end of a half-life, I'll be down to 50, and that takes 1,590 years. I used that to create an equation which allowed me to solve for my b value. I then was able to use that b value and the a value they gave me, along with the amount of time, to solve for how much was remaining. We have just one more problem. We've been working with y equals a times b to the x, or y equals a times b to the t, but it's also pretty common to use e as a base. So if you're given a problem in the form p of t equals p sub 0 e to the rt, so p sub 0 is going to be the initial value still. We're going to use e as our base. R is going to be our relative growth, written as a percent. Sorry, written as a decimal. And then it's going to give us the growth rate relative to the current population. So it's not the same growth rate as we saw before. The number of bacteria in a culture is given by the function n of t is equal to 1,000 e to the 0.1 t, where t is measured in hours. What is the relative growth rate of this bacterium population? We were told that our relative growth rate is r, which is the number in front of t, so 0.1. But that's given it as a decimal, we want it as a percent. So 0.10 converts to 10%. We want to know what the initial population was. If we plug in t equals 0, we're going to get that population was 1,000. Finally, we want to know how many bacteria will the culture contain at time t equals 5. So they're just asking us to plug in 5 for t. So the population at time t equals 5 is equal to 1,000 e to the 0.1 times 5. 0.1 times 5. I'm getting about 1,648.72. That's all we got. So when it comes to these application problems, take your time, read the question, figure out what it's asking, figure out what it wants, work through it slowly, and ask questions if you have them.